Ders kaydını başlatmadınız sanırım.
Başlattım şu anda.
Tamam.
Dersi kayda başlattım. Geçen haftaya kadar arkadaşlar termodinamiğin 0. ve 1. kanunlarını gerçek ve ideal gazların genel makroskopik özelliklerini inceledik. Bir de kinetik moleküler teori dediğimiz teoriyle ilgili de çıkarımlar yaptık. İstatistiksel çıkarımlar da yapmıştık. Bu hafta itibariyle, yani geçen hafta itibariyle entalpiyi de cover yapacak şekilde, entalpiyi de içerecek şekilde termodinamiğin 1. kanununu neredeyse tamamladık. Tabii birkaç tane küçük şey var. Biz atladık. Mesela adiabatik değişiklikler var. Onları içermedik açıkçası, biraz daha komplike olur diye. Joule olayı, Joule-Thomson olayı dediğimiz olaylar var. Bunlar işte Joule olayı, free expansion dediğimiz olay, Joule-Thomson olayı, işte bugün buzdolaplarında çalışan o sistemde buzdolabının soğutma mekanizmasını açıkça anlatan olaylar var. Biz onları geçtik arkadaşlar. Çünkü onlar biraz kimyaya daha giriyor. Sizin biraz daha hani kenarından geçeceğiniz konular diye düşündüğümüz için o şekilde onları atlamış olduk. Bugün size second law'dan bahsedeceğim. Alright, let's start to discussion in English. And I would like to ask a couple questions to you before starting. Have you heard about the second law of thermodynamics? Is there anyone who knows what the second law of the thermodynamics is? No? No one? Hiç kimse yok mu arkadaşlar termodinamiğin 2. kanunun ne olduğunu bilen? Da söylemeyiz hocam. Ne gerek var ki? Diyor musunuz? Öyle mi diyorsunuz yoksa? Arkadaşlar termodinamiğin 2. kanunu entropi ile ilgili. Entropiyi duymuşsunuzdur ama. Termodinamiğin 2. kanunu olarak duymadıysanız bile entropinin ne olduğunu az çok duymuşsunuzdur. Okay, this is the motto of I like the way the second law of the thermodynamics is working. So some things happen, some things don't. This is the core of the idea of the thermodynamics second law. Okay, some events, either physical or chemical, are always occur themselves without any external force in one direction, but some events do not. So this is the way we actually say that the entropy is the force that is driving events to occur in one direction. Okay, so the second law governs is spontaneous change. What we call this is spontaneous change. Okay, spontaneous change. Spontaneous change is a change that has a tendency to occur without work having to be done to bring it about. Okay, so it is a natural tendency to occur. So it occurs itself without doing any extra force on it. And it occurs in only one direction. It doesn't go back. It doesn't do the reverse. Reverse is not occurring. For example, when we put gas in a container, the gas fills the container itself, right? We never see that we have a container in which there is a gas, but the gas is shrinked in some small space in this container and the rest of the container is empty. There is no such case. If you have a gas, it fills the container and it expands to fill it in one direction. I mean, it doesn't go back to shrink in some small location in the container. Or you can have like mine, you can have a tea. It always gets colder until the room temperature is reached. So this is the first zeroth law of the thermodynamics. Until the thermal equilibrium is reached, this has a tendency to cool down or getting colder. I mean, in terms of energy, there is no difference between the total energy of the system, as in case of my tea, plus the surrounding, the room's temperature, and etc. So once this tea gets colder, okay, the rooms gets hotter. So the heat flows from my tea to the surroundings. Okay, that's why the total heat in terms of the universe is constant, doesn't change. But we never see that the room gets even hotter, or the room is even getting colder, and my tea is getting even hotter. So when you leave it, your tea on the desk, you never see the tea gets hotter itself because of the heat flow from the room temperature to your gas system. I mean, cooling of this object is one way process, and it's always in the heat from the system to surrounding. So this is a spontaneously happening event. Okay, so there are some other examples you can give. I mean, if you have, for example, if you put two gas in one cup, okay, the gas starts mixing to each other. You never see that, or you never see the reverse process. You have a mixture of gases in a cylinder, for example. You never see the gases separated from each other itself. There is no such process, right? The gases are not going to be separating from each other itself, because the gases always tend to mix together. Okay, even if you put the gases at separate points in the gas cylinder, in the tank, or so you eventually see that the gases are mixing together. Okay, so the reverse of this process, in which you have a mixture of gas in the container separating the gas together, this is not possible itself. I mean, this is not going to do itself. To do this kind of job, you have to apply force, external force. Okay, when you leave the system without touching, always the gases flow to mix together. This is also one-way process. This is also a spontaneous event. Okay. So when you have like these two objects together, when you bring these together, according to the zeroth law of thermodynamics, we know that the heat flows from B to A, not from A to B. Energetically, according to the first law of the thermodynamics, the first law of thermodynamics governs the total energy of the system. So when you have A is even colder and B is even hotter, when you have their energies summed, so the total energy will not change. Either A is getting cooler and B is getting hotter, or A is getting hotter and B is cooler. So it doesn't really matter for the first law whether these objects are exchanging heat in one way or the other. But there is a process that drives this in only one direction, that limits this in only one direction, which is that heat is transferred from hot object to cold object, not from cold object to hot object. Okay. And that is actually what the entropy is governed. So for example, if you have the thermal energy of A is 10 joules and B is 30 joules, okay? So the total energy of the system is 40 joules, right? So if you have either A is 15, B is 25, or A is 5, B is 35, doesn't really matter. So either you are heating up A and B, or heating up B and A, cooling down A, doesn't really matter according to the first law of the thermodynamics. First law says that the total energy is constant. In each case, total energy is 40, which is fine. This is totally fine for the first law. But we never see such case that A is going to increase or A is going to decrease its energy and B is going to increase its energy. So we know that B is going to cool down and B is going to lose energy. Okay? So there must be another law, another thermodynamics law that governs or that tells us that why is this not happening, but this is happening, although they are energetic. Okay? If you have a gas, for example, over here that I was trying to explain it to you, if you put the gas in this container, you always see that the gases expand to fill the container. And this is spontaneously occur. The reverse is not occurring. If you put the gas in such container, for example, in a large volume of container, you never see the gas shrinks in very small space and the rest of the containers becomes empty. There is no such case. Okay, so this is non-spontaneous event. To do this, you have to apply force. So what is the rule that governs or that tells us why this goes to this direction but not this goes to this direction? Okay. Just like the other example I gave, if you have two different gases in one container, when you leave them without any wall between, so you start seeing the gases mixed together. This is a spontaneous event, but the reverse. I mean, if you start with such case, for example, and wait enough time or long enough or years, even infinite time, you never see the gases will come to a point where the blacks are on the one side, the blues are on the other side of the container. This is never occurring. And there must be some law that tells us why this is the case. Okay? This is actually entropy. So entropy is a new variable of state, and it's a measure of the disorder of the system. Okay? It's a measure of the disorder of the system. Every change of the isolated system, okay, increases the entropy. So this is very critical. And entropy, we define another thermodynamic parameter or variable that tells us the direction of the events. And it says that, okay, we have what we call entropy is a new variable of state. It tells us the disorder of the system, and it always tends to increase. The disorderness of the system always in the way to increase. Okay, so any naturally occurring events or any spontaneous event will have entropy increase, or the disorderness of the system increases upon the physical or chemical change that you are doing. If the system is not isolated, the entropy of the system may decrease only if the entropy of the surroundings increases more than system's entropy does. So okay, so what is important is that the first law was governing that the entropy, the energy of the universe is constant. Now this says that the entropy of the universe is increasing, not constant, but increasing. So we know the energy of the entropy of the universe, just like the energy of the universe, is sum of the entropy and surroundings entropy. So the system's entropy and surroundings entropy. Together, the sum will have to be increasing for the spontaneous events to occur. Okay, if the system's entropy is decreasing, then the surroundings entropy must increase more than the amount of the decrease of the system's entropy, so that the total will be still greater than 0. Okay. So the second law says the entropy of the universe, the systems plus surroundings, is always increasing in spontaneous events. So spontaneous events can occur in two different ways, just like mechanical and thermal works, thermal equilibrium cases. Now the matter tends to disperse in disorder. Okay, so the matter itself can disperse through the entire system, or energy can disperse through the entire possible states. Okay, so second law says that the entropy of the universe increases by either dispersing the matter or dispersing the energy or heat. So there are some other definitions of second law. Let's look at the Kelvin definition. So he says that no process is possible in which the sole result is the absorption of heat from a reservoir to its complete conversion into work. So this is another way of thinking that there is no such case that from hot source to work there is no direct conversion. Okay, there is no such a case in which heat is 100% converted to work. This is impossible. Okay, so there, what is possible? So there must be a cold source over here. There must be a cold source over here, and some of the heat has to go to cold source to have such cases. So in actually in the end of the first law, when we had talked about the heat and work conversions to each others, it is as you remember, if we have irreversible process, the heat conversion to work depends on the path that you are taking. And whenever the process approaches to a reversible process, this heat to work conversion becomes greatest actually in the case of reversible process. Okay, so if you have a process that is irreversible from A to state B, if you have very quick process or very irreversible process, so you convert some of the heat to work. That's true, but you can increase the amount of work that you produce by adding additional steps in between A and B, just because you are approaching to reversible case. In the reversible case, you have an infinitesimal amount of change in each step. That's why you get the maximum work with the reversible process. So according to this, no process can be exactly truly reversible. So there must be at some level, there must be some irreversibility in your processes. and this irreversibility actually brings the efficiency of the work that you are doing. Okay, so the efficiency can be increased by approximating your or approaching to reversible case, but you will never ever reach to a truly reversible case, as we said. This is just like an ideal gas. No such gas exists to be perfectly ideal, except you can get approach to ideal case when you change the temperature, pressure, and other parameters, as you remember. Just like that, no such process can be truly considered as a reversible process, but we can approach to reversible case by adding some small or taking very gentle changes during the process. From state A to B, we can apply the external pressure, for example, to be very small amount, so that the system is just like a reversible process. But there is no such case that's a 100%. So that impossibility of having a truly reversible process brings the term efficiency of the process. Okay, the work that we do or the work that we convert from heat is always related to some part of efficiency. So we have to describe how efficient your system is producing work. Okay, that actually question brings the scientists to discover this new thermodynamic parameter or variable, the entropy. Okay, so how do we increase the efficiency to 100% question brings a new definition to thermodynamics, which is called entropy. So Kelvin defines this entropy as no such case, no such procedure exists in which a 100% of heat is converted to 100% to work. There is no such case. This is the definition of Kelvin. Actually, Clausius defines the entropy in a better way, in a actually much better way. Heat does not flow spontaneously from a cool body to a hotter body, he says. Okay, so it says the heat never flows from hot object to cold object, from cold to hot object, but it is so this is not possible, this is impossible to do, but the reverse is always happening. That is another way of looking at the entropy definition actually. So these two definitions, Kelvin and Clausius, can be pictured in this case. So you can have such system in which you produce work from hot source or from heat by wasting, I mean, spending some of the heat or by wasting, I mean, israf etmek arkadaşlar. İsraf etmenin başka Türkçesini bilmediğim için, başka kelimeyi bilmediğim için söyleyemiyorum, özür dilerim. You have to have some waste of heat to convert heat to work. Okay, that is the efficiency actually that you are dealing with, that I have been talking. So this is a possible case. So if you did not have a cold sink over here, this process wouldn't be possible. But now if you have a cold sink and heat flows from hot to cold and to work, so you can split heat into work and a little bit of heat waste. Okay, so this is possible, and this is called heat engine. The reverse is also possible. If you have a cold source and hot sink, you can do work on the system, and you can have heat transferred from cold source to hot source. So you can do the Celsius example by applying a work over here, or you can do the Kelvin by putting another cold sink over here. Okay, but not the case. This is not possible without doing a third, or without wasting some of the heat, let's say. Okay, so for the second law, we have to think together the surroundings and system together. So far we have described the surrounding, but we never looked at the surroundings, what's happening in the surroundings. Instead, we tended to measure the changes occurring in the system instead. But now, for a process to be spontaneous or not, we have to look whether the entropy of the entire universe increases. So we have to look the system plus surrounding entropies. Okay, so we can say as total is actually systems plus surroundings, and the total has to be greater than 0 for the system or for the one-way processes. Okay, or spontaneous processes. If you could catch the idea that for a reversible process, so if you remember what the reversible process is, we defined the reversible process to be exactly at equilibrium of system and surroundings, right? And the reversible process can go either one way to or to the others by infinitesimal amount of external force applied on the system. So for a truly reversible process, the entropy actually is 0. Okay. Since we cannot get a truly reversible process, all of the processes will be at some level will be irreversible. So the entropy of the universe must be greater than 0 at some level. Okay, so it can either be equal to or greater than 0. It can be equal to only in the case of a truly reversible process. So okay, now we can say that the entropy of the universe increases in irreversible processes. That's also another definition actually. For irreversible processes, the direction of the process is governed by the entropy of the universe. If the entropy of the universe is greater than 0, that process occurs itself, and it is, since it is occurring itself, it is already an irreversible process. Okay, so let's define the thermodynamically what this definition can mean in terms of other thermodynamic parameters. So energy and matter dispersion in a disorderly way as heat, not work, is defined as entropy. And the mathematical definition of entropy, thermodynamic definition of entropy, is given by ds is infinitesimal amount of entropy change, is infinitesimal amount of reversible process divided by temperature. Okay, so Q reversible is the energy transferred as heat reversibly to the system at the absolute temperature T. Okay, so delta S is defined by a perfect reversible process. I mean, we will imagine that our process as if it was occurring reversibly. What would this heat be? Or what would the maximum work be? or what would the efficiency 100% be? Okay, how? So we can drive this in accordingly. So if what would happen if I had 100% efficiency, or if I had maximum work done, or if I had a reversible heat change? Okay, so this is the definition at the absolute temperature T. This is the definition of the entropy. Okay, so entropy is just like internal energy, and enthalpy, it's also a state variable. So for the state variables, we remember we can put a delta sign. So it does not care about the path or intermediate steps that you are doing. It only cares about initial state and final state, which is very nice. So it only cares about the initial state and final state. And the definition is given by delta Q reversible over temperature, absolute temperature. So how do we find the delta S? Now there are three steps that we do. For I and F states, or initial and final states, find a reversible path. Okay, for any process, find a reversible path that does this change. Then integrate energy supplied as heat at each state. Okay, divide by temperature of at which heat is transferred. Okay, then collect them all to find the cyclic entropy change, which is going to yield as the total entropy change. So entropy is also extensive, just like the delta H and delta U, but when we can put M sign over here, change it to molar entropy, which will become the intensive variable. So let's do an example. Okay, calculate entropy change of a sample of perfect gas when it expands isothermally from initial volume to final volume. Okay, so this is from first law. This is what we know from the first law. Okay, and Q has to be minus delta W, minus W, and Q reversible has to be work reversible. So work reversible means the P external has to be equal to P system. So for the reversible cases, P external becomes P system, and P system is given by for perfect gases with this formula. So we can write the Q reversible as P dV, and P is nRT over V dV. So T is constant because it's an isothermal process. So now N constant, R constant, and T constant. So what we have is dV over V. So delta S becomes from initial volume to final volume, and RT over V times dV divide by T from the definition. Okay, this is from definition. So when we divide by T, the T's will cancel out, and NR is constant and will be coming out to the we can take out of the integration sign. So what we have, dV over V. So dV over V will be integral of dV over V ln V. So V final, this is a definite integral, ln V final over ln V initial. So this is what we for the entropy change of the system during such process. Okay.
Hocam ben bir şey sorabilir miyim?
Yes.
Bu şeyden sonrasını anlamadım. P ekstra eşittir P sistemden sonrasını anlamadım.
P external equals to P system, and P system is given by this law perfect gas law and RT over V. Arkadaşlar şimdi birinci kanuna göre biz bunu biliyoruz. Q artı V eşittir 0. Değil mi? Neden 0? Çünkü bir izotermal proses. İzotermal proseslerde perfect gazsa, bakın sadece perfect gazlarda 0. Diğerlerinde dediğim gibi Joule free expansion coefficient'ı var. Ona girmiyoruz şimdilik. 0. Dolayısıyla Q ne olacak arkadaşlar? Eksi W. Bunu eşitliğin öbür tarafına attım. Ben ne yapmam gerekiyordu? Önce bir reversible path bulmam gerekiyordu. Q o zaman reversible bir Q bulmam gerekiyor. Q reversible ise W da reversible olmak zorunda. W'nun reversible olduğu durum neydi? P external'ın P sisteme eşit olduğu durumdu. O halde P external gördüğüm yere P sistem yazabilirim. P sistem yerine sadece P de yazıyorum arkadaşlar. İdeal gazlarda sistemin basıncı NRT bölü V ile veriliyordu zaten. Ben o NRT bölü V eşitliğini şuradaki eşitlikte Px yerine yazabilirim artık. Çünkü Px P sisteme eşitti. Dolayısıyla ne oldu arkadaşlar? Benim Q reversible'ım neye eşit oldu? NRT bölü V dV'ye eşit oldu. Değil mi? Buna eşit oldu. Bu ney? W reversible. Eksi W reversible da Q reversible. Anladık mı arkadaşlar? Eksi W reversible olduğu zaman eksiyle şu eksi birbirini götürdüğü için buradaki eksi işareti de gidiyor arkadaşlar. Dolayısıyla ne oldu arkadaşlar?
Anladım hocam. Tamam. Anladım.
Buna eşit oldu. Şimdi burada yukarıda definition'ımızda da temperature vardı. Temperature'a bölmem gerekiyor ben buradaki reversible prosesteki Q'yu. Reversible prosesteki Q bu. Bunu temperature'a böldüğüm zaman temperature'lar birbirlerini yok edecek. N sabit, R sabit. Bunu integralin dışına alıyorum. Geriye kalıyor dV bölü V. dV bölü V'nin de integrali bu şekilde bulunuyor arkadaşlar. Dolayısıyla bunu molar büyüklük olarak yazarsak, yani şu N'yi bu tarafa bölüm olarak atarsak arkadaşlar, delta S'yi de şu anda intensif bir büyüklük olarak bu şekilde tanımlayabiliriz. Okay. In this case, in another example, calculate delta S when pressure of a fixed amount of perfect gas is changed isothermally. Okay, this is again isothermal event. But instead of volume change, now we are doing pressure change from P initial to P final. Okay, so for isothermal process, I will write again the same formula. I will start with the same formula. We'll go to the same points as I did in the case of the other example. But over here now, my question is asking from PI to P final, not VI to V final. If it was VI to V final, I would do this one. But now I will have to do a little bit trick over here. For perfect gas, I know that PV is a constant term. So if I take the derivative of PV term, okay, so derivative of a multiplication is actually is chain rule. Take one constant and take the derivative of the other one, plus take the derivative of the first one and keep the second one constant. So I can do this as I can expand it to like that, but I know that the PV is constant and derivative must be constant. So if I take this one of them to be the other side of the equation, I can have such a result. So this is what I needed to do, because I am now using the pressure change, not the volume change. I am monitoring the pressure change. But I can define the pressure change in terms of volume change. Okay, so delta S now becomes from P initial to P final, times P times dV over T, just like over here, nothing different. But now instead of P times dV over T, now I know dV is V dP over P minus V dP over P, right? So dV over here, I can extract dV over here and put it in this equation right here. So which is V dP minus P divided by minus P. V dP divided by minus P over here. Okay. So if I can write, I don't know whether I can write. So, okay. So this will be P times V dP divided by minus P. Okay. Of course, T is over here also. So T is over here also. So the P's will cancel out over here. Okay. What I have left is minus V, right, dP. That's what I have left. So I can take the integral again and do the same thing to find out NR ln PI over PF. Okay? Yes. Okay. So far we have discussed the entropy change during the isothermal processes. But if temperature is also changing, what's going to happen? Okay, so if I have this definition and T over here is the absolute temperature, but this cannot be directly used when temperature is also changing. So then we have to come back to our original definition of entropy and derive an expression for temperature change to include temperature changes. Okay, so the delta S becomes now the dq reversible over temperature. So there is negligible error in temperature because it changed infinitesimal amount. So it was a dt. It was a normally. So normal definition would be over here dt, but since this is at absolute temperature and temperature change, very small amount of temperature change does not really impact the result, we can ignore that infinitesimal change of the temperature. Actually, I would have to write this a little bit over here. So this would be normally, so this is the case, dq
Hocam kalemi inceltebilirsiniz aslında.
kalemi nereden inceltiyorum arkadaşlar?
Kalem seçeneği var yukarıda. Oradan bir deneyin isterseniz.
Kalem seçeneğine bastığım zaman bir şey çıkmıyor arkadaşlar. Bende kalemin şeyi çıkmıyor ya, size'ı.
Hocam bir de sağda var.
Sağda
Sağ
kalem var.
tarafta var hocam 2 tane.
Bu redact. Bu değil galiba. Bu mu? Yok arkadaşlar, bu kalem başka bir kalem. Bununla alakası yok. Bu şeyi öneriyor bana. Akrobatı öneriyor da. Bu highlight arkadaşlar. Bu kalem değil zaten. Neyse. Önemli değil ya. Şu an vakit kaybetmeyelim ona. Şimdi burada temperature'a bir plus terimi olacaktı. Evet. Şöyle yapsam daha mantıklı. Ne yaptık? İşte akrobatlaşmaya çalışıyor arkadaşlar şu anda. Ben de bunu sevmiyorum ama. Evet neyse. Artık yapacak bir şey yok. Ya gerizekalı ya. Şöyle yapayım da. Okay. Normal term would be like that, but since this infinitesimal amount of temperature is really not going to affect the result of temperature, so we can ignore it. Okay. Anyways, so okay, now let's look at the equation. So we know that this delta Q over delta T is defined by heat capacity, right? So it's either at constant pressure. If it's constant pressure, so this heat capacity at constant pressure will be. If it is a constant volume, this will be a constant volume heat capacity. But anyways, we are going to leave it open so that it can be either of them. So delta Q, now we can write delta Q as C times delta T. So for the reversible delta Q, it has to be C times delta T. Okay. So I can replace delta Q over here with this term right now. Okay. If I have delta S, now I can redefine my delta S by C times dt over T. So from initial to final volume, so this is going to be my equation. But in most of the cases, not most of the cases, some of the cases, the heat capacity at constant volume or at constant pressure is generally constant. Assuming constant, we can take this out of the integration sign and we can write such formula, and then we can take the integration and end up with such equation. Okay. So what does this tell us? Delta S is equals to C times ln T final over T initial. If my final temperature is greater than initial temperature, then this ln term, entire term, will become positive. And this is entire becomes positive, S will be positive. And this event is spontaneous. Okay. So let's calculate the delta S when water vapor is heated from 160 to 170 at constant volume. So assuming the constant volume heat capacity is 26.92 and it's independent of temperature, and so we can use this formula directly and now get the molar entropy change is given by this formula, and we end up getting plus 0.615 joules per Kelvin per mole. So when you look at the units of the delta S, it's just like energy. So it's joule per Kelvin per mole. So there is a per Kelvin term over here. So it is actually divided by temperature. the energy divided by temperature. Okay, so we said this is if we found this equation when we assume C is constant. But C is in most of the cases, C is actually a function of temperature. Okay, C is not constant. It's also a function of temperature. So you cannot take this out of the integration sign easily because this is also temperature dependent. So in this case, you have to keep the C inside the integration and then do your math again. Okay. So for those cases, we will have to use this formula. This is the ultimate formula that covers them all. Okay. So you don't need to specify it's CP or CV. You don't need to specify C is constant or not. This tells us everything. Okay. So if this is the general formula of heat capacity that we have shown in the past classes, I think in 2 or more classes before, we showed that the heat capacity is also temperature dependent, and it's going like this. For most of the regions, heat capacity is linear up to here, that point. The heat capacity is linear with temperature. So it's a first order polynomial. Okay, if I divide C over T, then I would get a constant volume up at this from this point to here. So from 0 to here, if I divide by C by T, I will get a line which is just like this. Okay, it would be going like that, just a line, a straight line, because like that, because C over T in up to here, it's constant, it's linear. So the division will give you a constant value. But let's look at the temperature change when we have when we look at the C over T, so which is this term over here, okay, and versus temperature change. So the area under this will give you the entropy because of this formula right here. Okay, so this term, C over T term, times delta T will give you delta S, which is the area under this graph. So if this was the T initial and this was the T final, then the area in between will give you the delta S. Okay, so let's do an example. So in this case now, the heat capacity is not constant. It is a function of temperature. So molar heat capacity of chloroform at constant pressure was found to fit this formula. Okay, this is the heat capacity formula at constant pressure. So this is valid between 20 Celsius and 37. So this point, let's say, is 37. So this is 37. So calculate the delta S. Okay, so what we need to do, the entropy at 310 Kelvin minus entropy at 293 Kelvin I need. So I need the integration, or the area under this is given by C over T times dt, and C is given with this formula right here, which is the function of temperature. I need to divide by temperature and then take the integration. So if I divide this part, I can separate from this part and then do the integration by parts, and I will end up getting this will be 91.74 times 1 over t dt. 1 over t dt will be ln t, which is this. The other part, in the other part, t's will cancel out, temperatures will cancel out, and dt will go directly at delta t. There is no ln part in this case because temperatures will cancel out in this case. So the resulting entropy change will be plus 6.45. Okay. Let's stop here. I will continue in, let's say, 20 minutes. Anladınız mı arkadaşlar? Şunu söyleyeyim. Ondan sonra 5 dakika içinde bırakalım. Ve 15 dakika bir ara verelim. 11'de başlayalım. Şimdi ne dedik arkadaşlar? Entropi değişimini nasıl tanımladık arkadaşlar? Entropi değişimini. En önemli bilmeniz gereken, burada bir sürü formül var tabii de. Bunların büyük kısmı formülün türetilmesi arkadaşlar. Tamam, bilmeniz gereken birinci formül bu. Ve bu formül tamamen bir konsept formülü. Yani bu eşitliğin ne olduğu ile ilgili bir formül. Q reversible'ı biz nasıl bulacağımızı biliyoruz. Ve Q reversible'ı biz her zaman C bölü T ile tanımlayabiliyoruz. C bölü T ile tanımladıktan sonra da bizim elde edeceğimiz entropi formülü arkadaşlar aslında bu. Kullanacağınız tek entropi formülü bu. Termodinamik olarak kullanacağınız. Yani termodinamik büyüklüklerden elde edeceğimiz entropi değişikliği bu formül kullanılacak arkadaşlar. Bu formülde hiçbir yaklaştırma yok. C constant pressure de olabilir, constant volume de olabilir. Sabit hacim, sabit basınç. C temperature'a bağlı da olabilir. Temperature'dan bağımsız da olabilir arkadaşlar. Her şekilde bu eşitliği kullanmam gerekiyor. Ama bu eşitlikte bir integral var almam gereken. Eğer C sabitse integralin direkt dışına çıkar. dt bölü t'nin integrali de ln t olarak çıkar. Eğer C sabit değilse, t'nin bir fonksiyonuysa ona göre işlem yapacağız. İşte burada da mesela C'nin sabit olmadığı bir örnek çözdük. 91.74 artı 0.075 çarpı t'ymiş fonksiyon halinde vermiş. Bunun ben integralini alırsam arkadaşlar, birinci kısmının integrali yine sabit bölü temperature 1 bölü t ln t olarak çıkacak. İkinci kısımda t'ler birbirini iptal ettiği için doğrudan delta t diye çıkacak. Ve sonuçta bu elde edecek. Yani sizin termodinamik olarak entropinin nasıl elde edileceğini sorulduğu zaman size kullanacağınız formül bu arkadaşlar. Bu entropi değişimi bu arada. Entropi değişimi. Termodinamik olarak entropi değişimi. Bu entropi değişimi arkadaşlar bu alana tekabül ediyor. C bölü T'ye karşı T grafiği. Çünkü burada C bölü T terimi var. Bir de delta T terimi var. Bu ikisinin arasında kalan alana tekabül ediyor. Bu matematiksel bir terim. Bu kadar. Bunu bırakalım. Burada bir 15 dakika sonra, 15-20 dakika sonra hatta devam edelim. Zaten evet 3'te 1'i bitti. 11. Yavaş yavaş yetiştirmeye çalışacağız arkadaşlar. Tamam arkadaşlar 18 dakika sonra buradayız. Tamam mı? Herkese uygun mu?
Evet hocam, olur.
Tamam. Ben şimdi kapatıyorum ekranımı ve mikrofonumu. Ama devam edecek arkadaşlar. Siz de çıkmayın bilgisayardan mümkünse. Çünkü kayıt devam ediyor arkadaşlar. Çıkmayın. Ya da çıkarsanız da tekrar girin. 18 dakika sonra tekrar girin arkadaşlar. Ama ben kapatmayacağım. Kayıt devam edecek. Görüşürüz arkadaşlar. Arkadaşlar döndünüz mü? Dönenler var. Dönmeyenler de var. 6-7 kişi eksik. Arkadaşlar şimdi entropi ile ilgili yani ister YouTube'dan ister şuradan buradan oldukça okuyun. Entropi çünkü biyolojik olayların cereyan etmesinde temel itici güç yani. Ve bu konu gerçekten iyi anlaşılırsa pek çok biyolojik event daha anlaşılabilir hale gelebiliyor. Şimdi biz tabii olayın kimyasındayız ama ileride örneklerimizde filan biyolojik olaylarda buna extend edeceğiz. Ve entropinin de aynı diğer fiziko-kimyasal büyüklükler gibi bir makroskopik bir de mikroskopik tanımlamaları var. Şu anda anlattığımız bu termodinamik yaklaşımdan entropinin belirlenmesi yine makroskopik büyüklüklerden yola çıkıyoruz. Ne yapıyoruz? Isı kapasitesini kullanıyoruz ya da ısı değişimini kullanıyoruz. Temperature'la, absolute temperature'la bölerek, oranlayarak hesaplıyoruz şu anda. Ama bu dediğimiz gibi makroskopik boyutta biraz sonraki bugün yetişir mi bilmiyorum ama sonraki şeyde mikroskopik konularda da yani entropinin o şekilde tanımı da var ve ikisi de benzer sonucu veriyor. Yani istatistiksel termodinamik dediğimiz tamamen mikroskopik seviyeden meseleye yaklaşıp moleküler düzeyden meseleye yaklaşıp aynı şekilde entropi hesabı mümkün. Şimdi ben şeyi de öneriyorum size ders başlamadan önce onu da söyleyeyim. Yani bu MIT'nin ben daha önce göstermiştim termodinamik dersi vardı. Oradaki lecture'lara da bakın arkadaşlar. Şu anda oradaki 8-9. lecture'lardayız. Ben şimdi açacağım hatta şimdi paylaşayım ekranımı. Evet. Şu an görüyor olmalısınız. Şimdi burada da çok güzel arkadaşlar yani çok güzel bir şekilde özet yazmışlar. Benim kendi el notlarımdan anlatıyorum ben size ama bunlara da göz gezdirin. Oradaki videoları dinleyin. Google'dan, YouTube'dan faydalanın. Başka kaynaklar var. Mesela bende 3-4 tane daha kitap var. Onlar da farklı şekillerde anlatabiliyor. Göz gezdirin. Yani göz gezdirmek zarar vermez. Sınıfta, dersten önce ya da dersten sonra ya sınava çalışırken muhtemelen Türklerin hepsi öyle yapıyor. Bir şekilde başka kaynaklardan da bakın arkadaşlar. Semboller değişebilir, notasyon değişebilir ama anlatılan içerik değişmez arkadaşlar. Aynıdır. Evet. Şimdi MIT'nin notlarına hızlıca bir göz gezdireyim. Ben sizde bir şey kaçırmayalım diye hani oradan eksik bir şeyimiz kalmasın diye de buradan da bakıyorum. Şimdi biz ne dedik? Birinci kanun dedik, değil mi? Toplam iç enerji ya da internal enerji Q ve yani ısı ve işin toplamına eşit. İş de zaten eksi P external çarpı dV'ydi. Reversible'larda P external, P sistem oluyordu falan filan. Ama cyclic bir proses için delta U'nun toplam değişimi bir cycle yapıyorsanız sıfırdı. Ve biz böyle delta U'nun cyclic prosesler için sıfır olduğu durumlara bir isim veriyorduk. Bu isim de neydi? State fonksiyonu değil mi? Hal fonksiyonu. State fonksiyonlar bu şekilde delta çevrimler sıfır veriyor arkadaşlar. Dolayısıyla cyclic proseslerde Q ne oluyor? Eksi W oluyor. Şimdi burada ben az önce anlatmadım. Yani atlayacağımızı düşündüm ama hızlıca bir göz atalım. Yine soru sormasak bile bunu da hiç bahsetmemiş olmayalım. Yarın öbür gün başka yerde karşısına çıktığı zaman bu neydi demeyin. Belki soru da sorarız. O da ayrı bir şey. Şimdi biz bunlara baktık. Evet. Direction of spontaneous change'i söylüyordu. Equilibrium state of the sistemle ilgili de bilgi veriyor entropi. Nasıl bilgi verdiğini şimdi söyleyeceğim birazdan. Kelvin tanımına bakmıştık arkadaşlar. Ne diyordu? It is impossible for any system to operate in a cycle that takes heat from a hot reservoir and converts it to work in the surrounding without at the same time transferring some heat to a cold reservoir. Yani bir kısım ısıyı israf etmeden ısının tamamını işe dönüştüren bir sistem dizayn etmek imkansızdır diyordu Kelvin. Bunu şematik olarak gösterdiğimiz zaman, ben de derste çizimimi göstermiştim, biraz daha burada güzel gösteriyor. İşte hot objeden doğrudan work'a giden hiçbir şey mümkün değil. Ama hot objeden bir kısım ısıyı cold'a götürürken o sıra iş mümkün. Bu possible, bu impossible arkadaşlar. İşte ki buradaki Q, W değişimleri de yazmış çok güzel bir şekilde. Clausius ne diyordu? Clausius nasıl deniyor onu da bilmiyorum telaffuzunda. It is impossible for a system to operate in a cycle that takes heat from a cold reservoir transferred to hot reservoir without at the same time converting some work into heat. Yani bu da şeyin tanımının neredeyse zıttı. Kelvin tanımının neredeyse zıttı. Bu da diyor ki öyle bir şey düşünün ki ısı tamamen soğuk objeden sıcak objeye doğru %100 akmaz. Asla akmaz. Dışarıdan bir kuvvet ya da iş uygulaman gerekir böyle bir şey yapabilmek için. Yani soğuk bir sistemden sıcak bir sisteme ısı akmaz kendiliğinden. Buradaki eşitlikleri de bu şekilde anlatmış. Clausius'un alternatif tanımı da all spontaneous processes are irreversible. Biz de bunu demiştik. Bütün spontane olan şeyler aslında irreversible'dır. Delta S'nin sıfırdan büyük olduğu bütün eventler aslında yazıldığı yöne doğru kendiliğinden yürür ve bu irreversible bir prosesi tanımlar. Delta S'nin sadece sıfır olduğu durumlar reversible prosesi tanımlar demiştik. Burada da matematiksel olarak da tanımlamış arkadaşlar. Reversible proses için cyclic delta S ne olması lazım? Sıfır olması lazım. Reversible proses. Ama irreversible proseslerde işte cycle Q bölü T sıfır olacak. Küçüktür sıfır olacak. Yani bu küçüktür sıfır, delta S büyüktür sıfır olacak. Sistemin entropisi çevre ya da surrounding'in entropisi ve ikisinin kombine olduğu evrenin entropisi. Bu kavramlar birbirinden farklı. Sistemde çevreyi topladığınız zaman evreni elde ediyorsunuz ve bu evrenin toplam spontane entropisi artma eğilimindedir spontane olaylar için. Yani evrenin entropisi artıyor. Çevreninki veya sisteminki değil. Onu unutmayalım arkadaşlar. Şimdi bir çevrim için delta S de yine reversible prosesler için sıfır olduğuna göre delta S de demek ki bir hal fonksiyonu arkadaşlar. Ve S2 eksi S1 şeklinde yazılabiliyor. Her zaman reversible proseslerde irreversible proseslerdeki Q'dan daha büyük bir ısı değişimi oluyor. Neden? Maksimum work oluyordu hatırlarsanız reversible proseslerde. Şimdi şöyle bir cycle yapalım demiş. Birinciden ikinciye giderken irreversible olarak gideyim. İkinciden tekrar 1'e geleyim ama bu sefer reversible olarak geleyim. O halde ben nasıl bir işlem yapmış oldum? Bir bakayım bu çevrimde. Birden tekrar 1'e geldim. Bir çevrim yaptım. Birinciden ikinciye giderken Q irreversible ekledim. İkinciden 1'e gelirken Q reversible bölü T yaptım. Toplam çevrim ise küçüktür 0 oldu. Birden 2'ye irreversible olarak yani yaptığım zaman eksi delta S küçüktür 0 oldu. Yani delta S 1'den 2'ye gidişin Q irreversible bölü T'si büyüktür 0 oldu arkadaşlar. Yani irreversible proseslerde delta S büyüktür 0 oluyor. Evet. Şimdi Kelvin ve Clausius statement'ları biz bu şekilde bir çevrim oluşturacak motorlar, engine'ler build yapmada, inşa etmede kullanılabilir arkadaşlar ki kullanılıyor da. Hatta bununla en yaygın kullanılan engine Carnot cycle'ına dayanıyor. Carnot cycle'ı duymuşsunuzdur belki bazılarınız. Öyle bir dizayn ediyorsun ki engine arda arda 4 tane proses yapıyor ve tekrar başlangıç noktasına geliyor. Önce birinci aşamada izotermal olarak sistemi 1'den 2'ye getiriyor. Sonra 2'den 3'e adiabatik olarak hala 1'den 2'ye izotermal olarak sistemi expand ediyor. 2'den 3'e sistemi bu sefer adiabatik olarak yine expand ediyor. 3'ten 4'e kadar izotermal olarak kompres ediyor. 4'ten tekrar 1'e kadar da sistemi adiabatik olarak kompres ediyor. Bütün path'lerin böyle reversible olduğu bir case senaryo hayal edersem arkadaşlar ne olur diye baktığımız zaman 1'den 2'ye gidişte izotermal olaylar olduğu için ve T1 sistemin sıcaklığının başlangıç sıcaklığının yüksek olduğunu düşüneyim. O zaman ne olacak? Delta U Q1'den buna eşit olacak. 2'den 3'e giderken Q eşittir 0 olacak. Çünkü adiabatik bir duvar var. Unutmayın Q değişimine izin vermiyordu hatırlarsınız. Delta U neye eşit olacak? W 1'in yani prime'la ifade etmiş. Çünkü tam bir buradaki kadar fazla bir vermiyordu hatırlarsanız. Eksi PDV değildi hani hatırlarsanız. 3'ten 4'e giderken de arkadaşlar T2'miz de biraz daha soğuk bir sıcaklık. Yine Q artı W. Ama 4'ten 1'e giderken de yine ve bunların bütün hepsini topladığım zaman arkadaşlar bütün enerji bileşenlerini topladığım zaman bana efficiency dediğimiz kavramı veriyor. Birinci kanuna göre internal enerjilerini topladığım zaman 0 olmalı. Bu benim state function'ım olduğu için 0 olmalı. Şimdi burada ne kadar iş üretildi diye sorulursa arkadaşlar burada işte ne kadar iş üretildi efficiency ile veriliyor arkadaşlar. Efficiency de çevreye yapılan iş bölü bir numaralı ya da sıcak objenin ısısı. Bu iki terimin birbirine oranı bize efficiency dediğimiz kavramı veriyor arkadaşlar. Termodinamiğin birinci kanununa göre delta U, cyclic delta U 0 olduğuna göre o zaman burada Q1 var, Q2 var. Bu ikisinin toplamı bu 4 tane W bileşeninin toplamına eşit olmak zorunda. Ve bu epsilonla efficiency'yi tanımlarsak eğer Q1 artı Q2 bölü Q1'dir arkadaşlar. Çünkü toplam işin toplam bir numaralı ya da hot objenin Q'suna oranıydı. Ve bu toplam işi ben Q1 artı Q2 ile yazabildiğim için direkt bu şekilde de efficiency'yi tanımlayabilirim. Efficiency'nin tanımı bu arkadaşlar. 1 artı Q2 bölü Q1. Yani bir termodinamik çevrim yaptığımız zaman bu çevrimde dikkat ederseniz efficiency her zaman Q2 bölü Q1'in oranında 100 ile 1 arasında 0 ile 100 arasında değişecektir arkadaşlar. Ve bu tamamen Q'lar tamamen başlangıç ve son sıcaklığın bir sonucu olarak ortaya çıkacaktır. Var mı? Kelvin tanımına göre bu şekilde. İşte bu şekilde arkadaşlar 100'den her zaman daha küçük olacaktır. Yani %100 efficient bir şey elde etmek mümkün değildir. Okey. Q2 her zaman sıfırdan küçük olacağı için bu oran her zaman birden küçük olacaktır. Dolayısıyla daha doğrusu eksi işaretli olacaktır. Birden bir şeyi çıkardığınız zaman da her zaman birden eksik, %100'den eksik bir rakam elde edeceksiniz demektir. İşte bu bugün bildiğimiz buzdolaplarının çalışma prensibi arkadaşlar. Tamam mı? Yani Q1 küçüktür Q2 bu şekilde buzdolapları nasıl daha da soğutuyor sistemi. İdeal gaz olsaydı ne olurdu diye burada detaylı bir şey var. Ben bunlara geçiyorum arkadaşlar. Ama ideal gazlarda da ben bunu ek ders olarak normalde geçen sene işledim. Bir ek ders yapsak bunun için işleyebiliriz. Ama siz bir göz atın arkadaşlar. Ben fazla bununla ilgili daha fazla bir şey anlatmak istemiyorum ama işte burada efficiency dediğimiz olay, entropi nasıl involve oluyor? Çok güzel bir şekilde bu Carnot cycle'ında anlatılıyor arkadaşlar. Okay. Now let's switch back to our original discussion about the entropy change during the physical and chemical processes. And we have discussed entropy change by the heat capacity times temperature, absolute temperature change. Let's look at what happens when we have a system changing or occurring phase transition. Okay. As we know, at phase transition from, for example, solid to liquid, the temperature is constant. So there is no temperature change. And the system's temperature and surrounding temperature becomes equal. Nearly equal. So if this, assuming T is T plus delta T, then delta S has to be plus. For a fusion process, for example, so instead of saying Q reversible for fusion process, now this becomes delta H of the, as we know, the Q is defined as H at constant pressure, right? Q reversible at constant pressure is the same as delta H reversible, so which is defined as delta H fusion divided by temperature fusion. Okay, so this is how we describe the entropy change during a phase transition. Okay, there is an example over here. For example, a lysosome a protein is at 75.5 Celsius. It goes to a phase transition. Okay. And the standard enthalpy of transition is given by this. Let's calculate the entropy change for this process. So the delta H is given. So we know the temperature transition, and we use this to find out the entropy change. Okay, let's calculate the entropy change of water vaporizing at 25 Celsius. Okay, so this question is a little bit tricky because it's asking me the phase change of water at 25 Celsius. We know that the water phase changes occur at 100 Celsius, not 25 Celsius, right? So, but the question is asking if I had vaporized water from liquid to gas at 25 Celsius, what would the entropy be? Okay, let's calculate this. So to do this, we can, since the delta S is a state function, we can set a cyclic or thermodynamic cycle in which we can take the liquid water and bring it to a temperature of 100 Celsius and then do a phase transition over there, because I know water is phase transition occurs at 100 regularly. So over there, I can get the gas at 100 Celsius. After that, I can cool down the gas to 25 Celsius with the pressure, of course, to get to the point which asks me this transition. Okay, so the entropy change for this, for the cycle 4, the 4-numbered process, is actually sum of the 1, 2, and 3 numbered processes. This is the same as the entropy change during this cycle. Because this is a closed cycle, it's a perfectly fine thermodynamic cycle, and I know the entropy is a state function, so I can. It doesn't really matter which way you go. It only cares about initial and final case. So in this process, 1 to 2 to 3 to over here, or it directly go from 1 to or number 4, doesn't really matter because initial and final states are the same. So the delta S4 will become the same as delta S1, delta S2, delta S3. Or we could write this, we could, instead of write this one like this, for example, if I have written this way around, okay, and now I put 4. So if I make a perfect circle, the arrows add up to make a perfect circle, then addition of them all will yield 0. So I would then do this equals to 0. Okay, so either you do a perfect cycle and then combine them all to make equal to 0, or you can reverse one of the path. You can reverse one of the path in the case over here, and all other cases yielding to the same direction as this will yield the same result. So the first process over here is a heating at constant pressure, and we can use this relation to find out the delta S1. The second process over here is a vaporization at boiling point, and over here we can find the delta S contribution. And the final process is a cooling process from 100 to 25 Celsius, which is given by this equation. Be careful about the heat capacities at constant pressure of liquid and gases. They are different. Okay, for liquid water, heat capacity at constant pressure is different than for gas. So use this term. We can find this heat capacities at constant pressures. We can find this from Google, or we can find from the website that I showed you last time, the NIST webbook chemistry website, or we can check up the physical chemistry books and the end tables that we can find from tables. So we can get this delta S4 as 118 joule per Kelvin per mole. Okay. So this is the entropy change in this system. What about in the surroundings? Okay. So as you remember, for spontaneous events, we have to look both of them, not just the system. So the same definition for the system can be used for the surroundings, but this time instead of Q system, I will have Q surrounding. Okay, and instead of T system, I will have T surroundings. So the temperature of surrounding and the heat that the surroundings exchanged. That's what's important in this case. So if you think about the surroundings, when you have a system, for example, like this, a glass of tea or water, so all the rest of the universe is surroundings. As you can imagine that the temperature of the surrounding is something really related to all rest of the universe, and it is really not changing a lot. When you have, even if you have huge changes in this system, your surrounding will be affected very little about this change occurring in the system. This is the nature of the universe, actually. This is the greatest size of universe. This is from them. This is the reason for having very little change in the surrounding is because the surrounding is too large comparing to your system, and the systems really affecting almost having almost no effect, very little effect on the surrounding. That's why the processes that take place in the surroundings is almost nearly reversible in all cases, because the change occurs is always very small or nearly zero. Okay, it is very small amount. If you have a very small amount of change, infinitesimal amount, what you are doing is you are doing reversible process, right? You remember that. So for the surroundings, we can drop the reversible case because all of the processes are assumed to be reversible in the surroundings because of the very tiny amount of change occurring in the surroundings. Okay. So actually the Q surrounding is minus Q system. So we can say delta S surroundings is minus Q system divided by T. T over here is the surroundings temperature, don't forget. At constant pressure, delta S surroundings is given by, since this is constant pressure Q is defined by delta H. So we can use minus delta H over T for the surroundings entropy change. So T is the temperature of the surroundings, not the system. This is a very important point. Okay. So for example, enthalpy of vaporization of water at 20 Celsius is 44 kilojoule per mole. When 10 centimeter cube of water in an open vessel evaporates at heat temperature, at that temperature, what is the delta S surroundings? So the delta S surroundings is nearly minus 83 joule per Kelvin. Okay. Okay. So far so good. We have discussed the second law in terms of thermodynamic parameters, and we have discussed that the delta S is another state function, and it depends on the temperature and the heat of the universe. Or I can split the delta S in terms of systems and entropy and the surroundings entropy, and the total entropy change was defining the direction of the event process occurring, or irreversible process, direction of the irreversible process occurring spontaneously, simultaneously itself. Okay, but let's discuss about the delta S. Delta S or entropy is not just like a regular thermodynamic variable. like delta U or delta H. It's even more than that. What's more is that delta S or entropy is something really that has absolute value. If you remember, for internal energy or for enthalpy, we said there is no such absolute values, and we instead use relative values. If you remember, for enthalpies, we were using or we were referencing the most stable forms of the molecules to be zero. We were always relating delta S or delta H, the enthalpy changes, referring to the formation enthalpies of the most stable forms. So it was always a relative variable, relative quantity. But now delta S actually, since it's a function of temperature, and I can extrapolate temperature to be the absolute zero value and see what happens to the entropy. So what if what happens if the initial temperature is zero? So if the initial temperature is zero, then I would get something really strange. Entropies of all perfectly crystalline substances are the same at temperature zero. This is so when we look at the C over T versus T temperature graph. So this was the area of T initial to T final was the entropy change for this process. So let's shift this T initial to this place over here. Okay, what's going to happen now is that I have such kind of process in which my T initial is zero. So my entropy will be over here. And for T1, I have such kind of, I can write this starting from 0 to 2, and I can write this process starting from 0 to T1. Now I can subtract the area of this one from this one to get the area of that one over here. Okay, so this is actually the delta S. But over here, there is this term over here. Since the temperature starts from 0, so this is S0 is basically is 0. So this goes to 0. It's interestingly, the S or the entropy at 0 point becomes 0. This is the definition of third law of the thermodynamics. Okay, the entropy at the absolute 0 is 0 for all substances. Okay, all perfectly crystalline substances are at the same, they have all 0 entropies. Okay, so as you remember, this was the delta S formula. Now instead of having T1, I will start from 0. So since this is 0, so instead of I will have, excuse me. Yes, this is going to be yielding 0 entropies at 0 kelvins. Okay, so third law was saying that entropy at 0 temperature is 0. So instead of using delta S values, okay, delta S values, which is defined as the entropy change for a physical event or any change, physical change occurring, I can have entropy to be the exact value. Instead of writing delta S, I can directly use S S is an absolute value, just like temperature. Okay. So let's look at the molecular interpretation of entropy. Okay. So far we have been discussing the entropy in terms of thermodynamic definition, and we were using the heat capacity over temperature integrated by different temperatures. But now let's look at the, as I told you earlier, that the entropy has a definition also from microscopic definition. So this is the great formula by Boltzmann. He found that the S, since I know the S now is something not relative, it's an absolute value according to the third law of the thermodynamics, and that absolute value can be defined as Boltzmann constant times ln W, which is the number of probability of states. This will be, I will define this later on. Actually, I would like to show you that this book just a sec. I will open this book over here, which tells us much better. So let me open this first. Okay. So where is it? Where is it? Yes, here. Okay. So using the macroscopic approach of thermodynamics, we have found that the equilibrium state of an isolated system is that the state in which the entropy has its maximum value. From a microscopic point of view, we might expect that the equilibrium state of an isolated system would be the state with the maximum statistical probability. Okay, so we will have, is it this one or that one? This one is actually, I was trying to find out. Okay, I was trying to find out this one, not the other one. Okay, so this is a little bit from microscopic point of view. The definition of entropy comes from statistical thermodynamics, or we will have to do some statistics and actually probability calculations. So we have to first discuss that probability of the outcome of a coin toss. You know coin toss. So it can come either heads or tails, and the probability of coming heads is 1/2, and probability of coming tails is 1/2. So this is for a single throw, we can say that it's 50% that heads will come, or the 50% tails will come. Okay. Okay. What if I have multiple tosses or multiple throws that I do? What is going to be the outcome of multiple times tossing? Or if I have multiple numbers of coins and I flip them all, what's going to be the result? So the total let's mark the heads as H and tails as T. So for combined probability of obtaining first head and 10, or let's calculate the probability of having two heads at the same time. It's 1/2 for each. So the probability of having both of them to be heads is as actually 1/2 times 1/2. It becomes 1/4. So only 25% of the cases I will have both of them are heads. So if I throw two dice at the same time, and I would two coins at the same time, and I would say, okay, what is the probability of having one head and one tail? It's the same. So for one head, it's 1/2. For one tail, it's another 1/2, and the result is multiplied by together to get 1/4. Okay. If I have, just a sec. Okay, let's okay. So if I have, let's say you have 4 coins. Okay, you have 4 coins, 4 of them. So let's calculate the probability of getting tail, heads, tail. So head, tail, head, tail. What is the probability of getting head in the first coin? 1/2. What is the tail of getting the second one? 1/2. And 1/2 times 1/2. So you have to multiply all of them together to get the resulting probability. So there are different probabilities. Only 1/16 of the probabilities will get you at this result. Okay. So let's actually, in fact, the probability of obtaining any particular sequence of outcomes in a series of 4 coin tosses, such as getting H, all of them to be heads, or all of them to be tails, are always 1/16, because each one of them has 1/2 probability. So this is 1/2 heads, this is 1/2 tails, 1/2, and the total outcome is HTTT, and the total probability is given by this. Okay, so for outcome of all of them heads, the total probability is given by this. For an outcome of 8 tail, heads, the same probability will have. Okay. You remember that when you sum all of the probabilities, sum of all of the possible probabilities must be 1. It must be 100%. Let's aggregate the outcomes. Okay, the most likely result is the one that has a maximum multiplicity. Now, instead of being concerned with the result of any individual coin toss, let's consider the aggregate or the net result of a series of coin tosses. Okay. For example, what is the probability of getting 1 head and 3 T in a series of 4 coin tosses? So I will have 4 tosses, and I'm asking whether getting only 1 of them head and 3 of them to be tails. What is the probability of this? So doesn't matter which one to be head or which ones to be tails, but I'm asking 1 head, 3 tails. So what is the probability? The number of the desired outcomes and the total number of possible outcomes is called, what is this called is multiplicity. Okay. So the number of desired outcomes is called multiplicity. How many different ways that you can have that result? For example, let's look at this. I did this toss, and all of them can be head. One of them can be tail, but each one, I mean, in this case, this one is tail and the other one's head. In this case, this one is tail and the other one's head, etc. I can have two tails and two heads, but it can be different ones. I mean, it doesn't have to be the exact ones. So I can have 1, 2, 3, 4, and 6 different ways of writing two tails and two heads, right? 6 different ways. And I have 4 different ways of writing three tails, 1 head, and 4 different ways of writing 1 tail, 3 heads. And I have only 1 way of writing all of them to be tails. So the multiplicity over here is 1, the multiplicity over here is 4, and over here is 6, and it's 4 and 1. So the total must be 16. Right? And the probability of this is 1 over 16, and the probability of this is 4.4 divided by 16, because 16 different possible cases, and only 4 of them are belong to this class. So it's 25%, and 38% it will come 2 heads and 2 tails, and 25% it will come 3 heads and 1 tail, and only 0.106 or 1/16 is the probability of getting all of them to be head. Okay. So the probability, when we combine probabilities, when we add these probabilities together and we sum them, we will get the result 100%. Okay. So okay, let's actually take this further to instead of writing explicitly, we can formulate this, okay, by using the combination in mathematics. So the weight or multiplicity, okay, sometimes called weight, that's why we use W, is actually the m factorial, where the m is the total, m is the number of coin tosses, how many times you did this, or how many coins do you have, and n is the number of heads obtained. Okay, how many heads did you want to get? So it is given by this general formula. Okay, and the total different ways is given by weight is given by this formula. For example, if you have let's say 2 heads and 2 tails, let's try to find out. I have 4 coin tosses, and I would like to get the probability of getting 2 of them to be head, 2 of them to be tail. Then m factorial is 4 factorial, because there is 4 tosses, and 2 of them heads, 2 of them are tails, and the result will be 6. As we have seen over here, it's 6. Okay. So this is the general formula for heads and tails coin tosses. Okay. So this is this explains why this is the case. I mean, why we are using the factorial, and how, I mean, what is the, how did we end up getting factorial from this picture over here? There is no relation, but let's look at in detail. When we look at this, we will see that if we have 4 coins in this one, picking one will have 4 different. You have 4 different choices. Once you have picked one, you have left 3 choices. Okay, and once you have picked another one, you have left 2 choices, and once you have picked 3, you have left only one choice. That is why 4 times 3 times 2 times 1 is actually 4 factorial. That's why we use m factorial over here. Okay. So you can even distribute all of the possibilities over here. It's distributed all 24 different outcomes of this. So you pick the number 1 in the first case. Now in the second case, you can have 3 different possibilities. You pick the second one in the second case, and then etc. You can understand the idea. Okay. So as you can see, there are many different outputs that you can get once you have only even for 4 tosses. You can have up to 24 different cases that you can have. Only some part of them, only 6 of them, let's say, are heads, 2 heads, 2 tails. But as you see, if you have increased the number of heads and number of tails almost nearly the same, so you will get more of the probabilities. If you have all of them to be tail, you will get 1/16 probability. If you have all of them to be head, you will get 1/16 probability. It's very small. But if you add 1 head and 3 tails, the probability is increased. If you had 2 heads and 2 tails, the probability is even increased, right? So the probability goes from 1 to 4. Oops. Just a sec. Yes. So probability goes from 1 to 4. 1 to 4 when you have heads and tails mixed together in a way that is distributed evenly. Okay. That actually is something related to something very related to the statistical definition of entropy. Okay. So if you have, for example, the same analogy can be used for any biological process. If you have a receptor-ligand interaction, for example, they can be used as an analogy between the coin tosses and receptor-ligand interaction. If you have a monomeric receptor, okay, so I can say tails is the empty ones, and its probability is 100%. So when we had heads, its probability is 100%. But for a dimeric receptor, if I have 1 ligand bound, I can have 2 different cases. If I have no ligand bound, I have only 1 case. If I have 2 ligands bound, I have only 1 case. So if I have a dimeric receptor and I have a ligand binding to dimeric receptor, so 1 ligand to 2 dimeric form creates more probability, okay, than 2 ligands or no ligands bound to the dimeric receptor. So this is just like that. This entropy of this one is greater than the other ones. Okay. So this is actually this is going even further, but let's this is the Pascal's triangle that you have seen, I believe, in the past in your high schools. That this for the binomial distribution, if you have 1 to 1 start with, So you will end up getting 4. Okay, so it's 1 head, 1 tail. So you will get, if you have 2, you will get 4 different possible outcomes, and 4 becomes like 8, and it goes like that. Okay, as you see, if you have 4, for example, 4 coins, 4 coins. So the first one, which is all tails, is only one case. 1 tail and 3 heads, 4 possibilities. 2 heads and 2 tails, 6 possibilities, and so on. As you see, when the heads and tails are coming nearly equal to each other, the probability increases a lot. If you go even further down to 10, for example, so you have 252 cases in which 5 of the heads and 5 of the tails will come. Okay? So when you compare them, if you have 10 different coin tosses, 10 different coin tosses, the probability of getting all of them to be heads is only 1 out of all this amount of all different probabilities. Okay, so how many different ways exist is actually, for each one there is 2 possibilities, 2 to the power of 10. What makes the 2 to the power of 10? Okay. So 2 to the power of 10. So you will get 1,000 different outcomes. So over here, if you have 10 coin tosses, you will get 1,000 in total over here. But only one of them will have only heads. So having heads is actually oops. Only 0.1%, 0.1% is the probability of getting all of them heads in 10 different coin tosses. Okay, so as you see, this is very small amount compared to all of them to be, or 5 of them to be heads and 5 of them to be tails is given by this formula. Okay, where is the formula? Let's change. Yes, here. This formula right here. Okay, so you can get the idea. So the Boltzmann tells us the natural logarithm of that probability that we have calculated from that is directly related to the entropy of the system, the entropy. So with it is a linear dependent, and the constant is the Boltzmann constant. Multiplication by Boltzmann constant gives the entropy. Okay. So if we have, for example, if we have all of them to be heads, okay. So the probability of getting that is 100. If we have 100% of probability, then the S becomes 0. Okay, so having the probability 100% means that there is no disorderness. It's a perfectly ordered. Its entropy is 0. Okay, so let's do one example in my book. If we have 10 molecules and 2 energy states, okay, I have 100 molecules and 2 energy states. I would like to put 100 molecules into 2 energy states. How many different ways of putting 2 molecules in the first state and rest in the ground? So 2 molecules in the first excited state and rest of them to be in the ground state. How many different ways of achieving this? So there are 100 factorial different ways, and 2 of them will be in the excited state, 2 factorial in the excited state, and there are 98 different factorials in the ground state. So there are 49, 50% or the total probable ways of putting 2 molecules in the excited state and rest of them in the ground state. So how about 3 molecules? Let's put 3 molecules in the excited state, in the first excited state, and 97 of them to be in the ground state. So when you look at this, the population or the weight, the W over there, grows tremendously. Okay, it increases from 4,000 to 160,000. It's going too very fast. What if I put 50 molecules in ground state and 50 molecules in the excited state? Okay, let's calculate this one. So this one will give you such enormous number, and that enormous number is actually 2 to the power of 100. So there are 2 to the power of 100 different ways of writing 50 particles or molecules in the ground state and 50 in the upper state. As you see, the number increased tremendously. So for this reason, when you have a system in which the gas molecules try to distribute all over the space, this is the reason why when you put 2 molecules together in a container, they start mixing. This is the driving force, because there is more probable way of writing this particle in this mixed state or in this larger volume space. Okay, that's the driving force, and this is how we calculate. So let's say we have a macro state in which the molecules are what we call ordered. So the blues are on this right hand side, the blacks are on the left hand side, and another state what we call disordered, or in which the blues and blacks are mixed together. So we have 2 different states, let's say. Okay, if we put if we calculate the microstates, the number of probable ways of writing this ordered way is given by this formula. Okay, but over here we can write n factorial different. I mean, let's say we have total n molecules, the number of the Avogadro's constant. We have n molecules. Half of them, or n over 2 of them, are in the ordered way on this side, n over 2 on the other side will be. So the total probability of having or writing this in different ways is probability of changing this. Okay, the order of this in each other's. So it's n over 2 factorial, and over here it's also n over 2 factorial. But in this case, since we have total n molecules, there are n factorial different ways. So the entropy of this state, if the entropy of this state is defined by K times ln W, so W is this over here. For the final state, the K times ln W becomes now this state. So from the initial to final state, the delta S is given by K times ln V final over V initial and n factorial divided by n over 2 factorial times 2. 2 times, or n over 2 factorial times n over 2 factorials. So which is ending up, we can do the math and find out K times ln 2 to the power of n. Okay, or n can be taken out, and K times n times ln 2 is the entropy change from the ordered to disordered case. As you can see, this result over here will be always positive, and if the number increases, the delta S will be increased, so the disordered way will be always preferred, and actually 2 to the number of n. So if you calculate we had only 100 molecules, let's say. If we had 100 molecules, so this much of probable ways of writing in the disordered way comparing to the ordered way. Okay, so let's divide 1 over 2. Let's do 1 over 2. No rest. So as you can see, 7.8 times 10 to the minus 31 is the probability of getting this state, and all of the rest of them are in this state. So which one would you observe in such different probabilities? So the probability of getting the ordered way is 10 times minus 31. It's almost impossible to get there. This is the probability. And probability of getting the ordered way is actually is minus 1. This one. So 99.999999% of getting disordered state. That is why when we have a system in which two gases separated each other, the system goes or evolves itself spontaneously to the disordered case, just because the probability of getting in the disordered case is 99%, 999999. Okay, and it's going up to power of 31. That's why we, instead of observing this case, we always observe this case when we leave the system itself, or when the system spontaneously evolves. Okay. Okay, I am almost there. Let me, yes, residual entropy, there is. Okay, Gibbs free energy. I'm not going to talk about Gibbs free energy today, maybe next week, but let's look at another example. If you have a perfect gas that's isothermally expanded to double its volume, what is the entropy change? From a thermodynamic perspective, you remember the thermodynamic perspective we have discussed in the first class of this today's lectures. We use V initial to V final, and we did delta Q reversible divide by temperature, and over here, since U is equals to Q plus W and isothermal event U is 0, and that Q reversible has to be plus P times dV, and this is a perfect gas. Instead of P, I can write nRT over V, and I can find delta S nR ln V final over V initial. So V final is 2V V initial is 1V, and I can end up getting delta as NR ln2, right? Let's look at this, the same example. Instead of doing thermodynamically, let's use statistics. Let's do the statistical point of view. So in the initial case, I have k times ln n factorial divided by n factorial times 0 factorial, which is 0. Okay. In the final case, I have k times ln n factorial divided by n half factorial and n half factorial, because in here, all of the n particles at over here, there is 0 particles over here. But in this case, half of the n particles will be in this space and the other half will be in the other space. So all of them to be in this and 0 of them to be in the empty space. Over here in the final case, half of them in the first part, the other half of the molecules will be in the other half. So using the same approach, using the same equations, we can find k times n ln2, and k times n, since we know this rule, n equals n times Avogadro's constant and k equals r over na. So k times n is actually n times r. So instead of k times n, I can write n times r and ln2. So as you can see, both results are exactly the same. Okay, using either thermodynamical approach or statistical approach, I ended up getting the same result for such an expansion. If I have isothermal expansion of gas from volume V to 2V, I will have my entropy changed by this. So the entropy of the system will increase. The disorderness will increase. The number of molecules that can have possible volumes to visit, probability of having particles in different volumes will increase. This is the phenomenon. That's the entropy increase. When you increase the size, change the volume, the entropy tends to increase. So if I had in this case, if I had, instead of having this line over here, if I had a piston over here, that is allowed to go back and forth, and vacuum over here, so I would know that this gas would expand until this piston goes to here, because this is the vacuum, and this goes, this gas expands from this case to this case. So this is the actually definition of irreversible expansion. This is an irreversible expansion. Okay, let's stop over here. Actually, I'm not going to go more. There is one more term that's called residual entropy. This is occurring in molecules, but this is a little bit more statistics and more involved, more careful. Yeah, we have to be a little bit more careful about calculating the entropy, because there is what we call residual entropy, in which the number of possible arrangements are limited by the unequal environments. You can have, for example, you can, let's discuss this in the next class, okay? Let's not go into this now. Ya da şimdi mi söylemeliyim arkadaşlar? Yeah, I don't want to have statistics left over. Let's discuss this for now, for a couple of minutes. Okay, in most of the cases, at temperature 0, the W is 1, just because there is no motion, there is no different degree of freedom to visit. That's why the weight is always 1. And since the weight is 1, natural logarithm is 0. Okay, and the entropy is 0. Remember, the entropy was K times ln W. ln W, if the ln W is 1, ln W, logarithm of W will be 0. But sometimes sometimes even the temperature is 0. There is one way of, there may be more than one way of arranging particles in this at exact 0 temperature. So this number of arrangements comes from the nature of different orientations or different environments that the molecules can have. What we call this is residual entropy. It's a small number. It's very small. So ideally, the entropy is 0 at temperature 0. But in some cases, it's not 0 because of the residual entropy term. So let's try to understand what the residual entropy is. If you have OH or water, okay? So the water has oxygen-hydrogen distance over here, which is the bond distance, okay? And over here is also bond distance. But there is also another OH from another water molecule. There is hydrogen bonding between these two molecules. And this bond distance, the hydrogen distance, the hydrogen to oxygen distance is not the same as the OH distance over here, because there is a covalent bond over here, but there is no bond over here. There's only hydrogen bonding interaction over here. So this distance is greater than this distance, right? So in such case, for example, there are two distances that are short, two distances that are long. If you assume only 4 of the 4 hydrogen atoms, let's draw this circle. If I look just these four hydrogens and 1 oxygen atom, there are 2 hydrogens that are long distanced, 2 hydrogens that are short distanced. Okay, so the combination of 2 long and 2 short distances is actually non-zero. Okay, this is not 100%. There is a little bit different ways of writing. So there are totally 16 different probabilities, first of all, but only 6 of them will have 2 short and 2 long probabilities. So not all configurations are acceptable. Only 6 over 16% of them are acceptable. I mean, you cannot have 3 short distances and 1 long distances in such molecule, right? You cannot have 3 long distances and 1 short distances. So you can only have 2 short distances and 2 long distances. That is only the acceptable value. That is why over the 16 different possibilities, only 6 of them are acceptable for such kind of molecule. So this is actually, if you have n number of molecules, in n number of water molecules, you will have 2n number of hydrogen atoms. Okay, so there are 2 to the 2n possible configuration, but only 6 over 16th are valid and make sense. The other ones are not really chemically make sense. Okay, so if we count the acceptable one and find out the weight or statistical weight of them, we will get actually 3/2 to the power of n. Okay, and since this is 3/2 to the power of n, and I know the entropy is given by k times natural logarithm of this part, the weight, so I can end up getting n times r times ln 3/2. So instead of ln1 over here, I got a little bit more than 1. So that it's not giving me a 0 value, it's giving me some value. And that some value for water is calculated to be 3.4 joule per Kelvin per mole. This is called residual entropy. This occurs in especially amino acids with different conformers that they can have. Okay, the hydrogen bonding among them. This is bringing a little bit residual entropy to the system. We are not, in ideal case, it is actually going to be 0 because there will be only 100% of molecules that are at the same exact state. But even at 0 Kelvin, too short and too long distances are possible in such molecules. So entropy at 0 Kelvin is 0 for only perfectly ordered crystalline structures in which all the bonds are equal to each other, okay? Because there is no disorderness in the molecule. But the molecules like water or others, or like what we call covalent crystals or other disordered molecules, will have some residual entropy. Okay, let's stop over here and I will start discussing the Gibbs energy when we come next time. Sorusu olan var mı arkadaşlar? Ben hızlıca 5 dakika gitmeden önce yine Türkçe ile söyleyeyim arkadaşlar anlattığımız şeyleri. Entropinin birinci dersimizde entropinin termodinamik tanımını anlattık. Entropinin tanımını da ne yaptık arkadaşlar? Her zaman kullanacağımız formül ne olacaktı? Kullanacağımız formül her zaman entropi isterseniz Q reversible bölü T üzerinden, isterseniz de heat capacity bölü T, yani C bölü T. Şimdi buraya gelmeden önce evet. Evet, burada işaretlemiştik. Bu formülü kullanacağız. Entropinin değişimini takip etmek için. Entropi değişimini tarif ettik ve termodinamik tanımı bu şekilde dedik. Her zaman bu formülü kullanacağız. Ama entropi dedik ki sadece entalpi gibi ya da iç enerji gibi, internal enerji gibi bir değişim, relatif bir büyüklük değil, aynı zamanda bir absolut bir büyüklük. Aynı temperatür gibi. Dolayısıyla 0 Kelvin'deki entropiler de yani delta ile illa ifade etmek zorunda değil mi? S'in kendisini de bulabilirim demek bu. 0 Kelvin'de de entropi değerlerinin 0 olması gerektiğini termodinamiğin 3. kuralı bize söylemişti. Ama tabii residual entropi dediğimiz entropiyi daha sonra tanıttığımız gibi 0 Kelvin'de de bazen 0 olmadığını gösterebiliyoruz. Ama neticede termodinamik olarak entropinin değişimini bu şekilde hesaplayabiliyorum. İstatistiksel olarak da olası bütün olasılıklardan yararlanarak, yani sistemin o konfigürasyonda olmasının toplam ihtimalinin doğal logaritmasını alarak Boltzmann sabitiyle çarptığım zaman da entropiyi direkt hesaplayabiliyorum. İster termodinamik açıdan, ister de istatistik açıdan entropiyi hesaplarsam aynı sonucu elde etmem gerekiyor. İşte S eşittir K çarpı ln W. Boltzmann'ın mezar taşında bile bu yazar arkadaşlar. Bu W dediğimiz şey bazen weight diye geçer. Yani ağırlık. Hani sizde ağırlıklı ortalama diyoruz ya, weighted average. Oradaki weight gibi. Bazen multiplicity diye geçer. Multiplicity, olası bütün ihtimaller ya da probability ya da probability density diyelim biz buna. Yani daha olasılık yoğunluğu diyelim. Bunların her şekliyle de tanımlayabiliriz ama biz genellikle weight'i kullanıyoruz. Statistical weight diyoruz biz buna zaten. Number of microstates ya da number of different ways molecules can arrange for the same total configuration or total energy. Bu şekilde bunu da kullanarak hesapladık ve bir moleküllü ya iki molekülü aynı sistemin içerisine koyduğum zaman neden birbirlerine karıştığını istatistiksel olarak da biz bunu gösterdik. N tane molekül için, 100 tane molekül için bile 10 üzeri eksi 31 oranında böyle düzenli durma ihtimali varken geriye kalan 99.99999 ihtimalde de böyle durması gerektiğini biz hesaplamayla da göstermiş olduk. Dolayısıyla neden bunu seçmeyip, neden sistemin buraya doğru aktığını, bu spontane olayın neden disorder yönüne doğru olduğunu izah da etmiş olduk arkadaşlar. Aynı şekilde bir gazı vakum olan bir sistem, yani bir sistem içerisinde bir volüme sahip bir gazı hacmini 2'ye çıkardığımızda ya da böyle 2V hacmindeki bir gazın arasına bir pistonla ayırdığımızda ve bu tarafı vakum yaptığımızda gazın neden expand olduğunu 2V'ye bu kabın tamamını dolduracak şekilde neden expand olduğunu da yine aynı şekilde istatistiksel olarak da gösterdik. Yani V tane molekül için gördüğünüz gibi 2 üzeri V N tane molekül için özür dilerim. 2 üzeri N farklı ihtimalle bunu yazabilirken bunun için sadece bir ihtimal, yani çok daha düşük bir ihtimal diyelim. Ne diyelim? Bu şekilde yazabiliyorum arkadaşlar. Dolayısıyla benim delta S'im yine buradan buraya geçişte artıyor. Yani entropi her zaman artmaya doğru yöneliyor diyelim. Entropinin artışı sistemin düzensizliğinin ya da serbestlik derecesinin daha fazla olduğu duruma doğru oluyor ve bu olaylar spontane bir şekilde kendiliğinden olduğu için bu olayların tamamı irreversible. Residual entropi de işte oksijen, hidrojen gibi mesela moleküler, yani bu entropinin absolute temperature'da, yani 0 Kelvin'de 0 olması gerektiğini söyledik. Ama bu ne içindi? Mükemmel ordered olduğu zamanlardaydı. Özellikle kristal structure'larda mükemmel ordered olduğu için ve bütün bağ uzunlukları birbirlerine eşit olduğu için orada bir residual entropi olmuyor ve de S mutlak entropi termodinamiğin de 3. kanununa göre 0 oluyor. Ancak moleküler kristaller gibi ya da yapısında disorder yapılar bulunan yapılar gibi yapılar olduğu zaman ne oluyor? Beklediğin mesela oksijen hidrojen arasındaki bağ uzunluğuyla bu oksijenin bir başka hidrojenle olan hidrojen bağ etkileşimi arasındaki uzaklık birbirine eşit olmadığı zaman bu işte order'a, yani düzene küçük bir düzensizlik ilave ediyor sisteme. Küçük bir düzensizlik tanıtıyor sisteme ve bu tanıttığı sistem, yani iki kısa bağ ve iki uzun bağ olmak zorunda olması sistemi birazcık ne yapıyor arkadaşlar? Olması gereken, yani entropinin 0 olması gerekirken artık 0 çıkmıyor. Bundan kaynaklı ilave bir entropik terim geliyor ve bu entropik terimi de biz bu şekilde hesaplamayı da size gösterdik. Su için mesela 3.4 Joule gibi küçük bir rakam bulmuşuz arkadaşlar. Dedik, Gibbs free enerjide kaldık. Haftaya inşallah buradan devam edeceğiz arkadaşlar. Haftaya belki bir ek ders daha yaparız ve o ek derste de ben size neyi anlatmak istiyorum? En çok Faz transition'lar. Evet. Phase diyagramlar. Faz diyagramlarını anlatmak istiyorum arkadaşlar. Ve kimyasal potansiyeli anlatmak istiyorum biraz. Onun için yetiştirirsem haftaya yetiştirmeye çalışacağım. Yetiştiremezsem dersin sonunda sizden bir ek ders daha isteyebilirim. Ama haftaya vizenizi veriyorum arkadaşlar. Diyoruz ve noktalıyoruz. Sorusu olan var mı? Konuyu dinledim ve anladım diyen var mı? Parmak kaldırsın arkadaşlar. El kaldırsın. Konuyu dinledim ve anladım hocam diyen. Gerçekten anladığını düşünen. 2 kişi mi var sana? Biraz olsun. Evet. Evet. Harika. Güzel. Güzel. Çok güzel. Güzel arkadaşlar. Anlamanıza çok sevindim. İnşallah hem sınavınızda çözeceğiniz örnekler, hem önümüzdeki hafta vereceğimiz ödev, hem de yine bizim ders örneklerle inşallah daha da pekiştireceksiniz bunları. Diyelim, noktalayalım arkadaşlar. Hepinizin ilgisi için teşekkür ediyorum. Kendinize iyi bakın. Haftaya görüşmek üzere diyelim. Kaydı
Görüşürüz.
durduruyorum.
Hocam haftaya şimdi sınav mı var yoksa ödev mi vereceksiniz? Ben onu anlayamadım.